Hello everyone. In the previous class, we have discussed about metals, semiconductors, and insulators. In today's class, we are going to see some fundamentals of electrons, which is going to help you to study the further module, the periodic table. The initial portion of the periodic table of elements may be determined by using the results of one electron atom plus two additional concepts. So there are two concepts here. The first concept needed is electron spin. The electron has an intrinsic angular momentum or spin which is quantized and may take one of the two possible values. So those values are, the spin is designated by a quantum number S, which can take a value of S is equal to plus or minus half. So we have basic four quantum numbers, namely N, L, M and S. The second concept needed is Pauli's exclusion principle. So we have studied this Pauli's exclusion principle in the high school level. So this Pauli's exclusion principle states that in interacting system, no two electrons have the same set of four quantum numbers. To describe quantum numbers, we must say there are four types of quantum numbers, and they are principal quantum number, which is N, azimuthal quantum number L, magnetic quantum number M, and spin quantum number S. So these four are principal methods of electron distribution in an atom. So using these four quantum numbers, electron distribution is done. Number of electrons, that is maximum number of electrons that can stay at any n, is given by 2n square. We have discussed this one previously. So the maximum number of electrons that can stay at any n, that is quantum number, principal quantum number n, is given by 2n square. So like for example, if n is equal to 2, the maximum number of electron will be 2 into 2 square, that is equal to 8. Now for any value of n, L must be from 0 to n minus 1. So remember, for any value of n, L value must be from 0 to n minus 1. For example, for n is equal to 2, L will be 0 and 1. Now for any value of L, M will be minus L to plus L, including 0. So for example, if M value is 2, then M will be minus 2, minus 1, 0, plus 1, plus 2. But here there exist only two states in S, and they are plus half and minus half. If the two electrons in an interacting system have all of these, that is N, L, M, same, then S of the two systems should be different in order to satisfy Pauli's exclusion principle. So this is the energy state notation. So the SPDF notations 1s, 2s, 2p, 3s, 3p, 3d are shown here. For n is equal to 1, 2 and 3. So whatever we have discussed just now. So if n is equal to 1, the range of L, M is given here. But S is, it has only two states, plus half and minus half. So for example, here for n is equal to 2. So L has 0 and 1, whereas M has, for 2s it is 0, for 2p it is minus 1, 0 and 1, and S has everywhere it is half state. So allowable state in subshell, for 2s it is maximum 2, for 2p it is 6. Allowable states in complete shell will be 8. This is an example. So inner shell and outer shell, total there are 8 allowable complete shell. We generally use different names to describe different azimuthal quantum states, like for L is equal to 0 we use S, for L 1, 2, 3 we use P, D, F respectively. When distributing electrons, we have to distribute them such that they occupy the lowest energy states. For example, for He atom, electronic configuration is 1s square, 1s2, and the outermost orbit is filled with electrons. So He is stable in nature. In case of Na, so this table shows that electronic configuration for the other atoms. For He, the electronic configuration is 1s2 and the outermost orbit is filled with electrons. So you can observe the atomic number and the what is the element and the electronic configuration of that particular atom. So for He, the electronic configuration is 1s2 and the outermost orbit is filled with electrons. So He is very stable in nature. So in case of Na's atomic number is 11. So its electronic distribution will be 1s2, 2s2, 2p6, 3s1. So Na has strong tendency to emit one electron. So for various atoms, the different electronic configurations are given in this table. So this is the electronic structure and energy level. So the figure shows orbital model of Si atom. The figure shows the orbital model of a Si atom which has a nucleus, a center part, a shaded part, a nucleus which is consists of 14 protons with a charge of plus 14. So along with protons, it also consists of neutrons, and it has 10 core electrons in shell. N is equal to 1 and 2 and 4 valence electrons in the 3s and 3p subshells. So it is distributed in the electronic structure and energy levels. So the inner orbit, valence orbit we can see, and we can see the core electrons and valence electrons, how they are distributed. So this is the electronic structure and energy level of a SI atom. So figure shows energy levels in the Coulombic potential of the nucleus that are shown schematically here. This figure shows the energy level of the various electrons in the Coulombic potential well of the nucleus. Since unlike charges attract each other, there is an attractive potential between the negatively charged electrons and the positively charged nucleus. The Coulombic potential varies as 1 upon r as a function of distance from the charge, in this case the SI nucleus. The potential energy gradually goes to 0 when we approach to the infinity. So we end up getting particle in a box states for these electrons in potential well. So similar to the general example, a mother and the boy. Mother who is outside the home, she thinks that her son may be doing a studies sitting on a table. She also may think that his son may be sleeping or he may be watching a TV. There are different probabilities what he may be doing. But when she comes to the home and opens the door, she finds that what exactly he is doing. Here also the same case with the electron. We can assume that where exactly the electron, we cannot find the position of the electron exactly. We can predict where it can be. What is the, if the value, maximum value, we can find there is a maximum probability that the electron may be present at that particular position. If the probability is 0, means there is no chance of finding the electron at that place. So location of electron, how to find the location of the electron? So unfortunately it is impossible to simultaneously measure the momentum and the exact position of an electron. Instead we can approximate, that is we can calculate the probability of finding an electron. So we can use the Schrodinger wave equation. So if we solve a Schrodinger wave equation for the SI atom, we can get a radial and angular dependence of the wave function or orbital of the electrons. Orbital of the electrons. Now let us focus on the valence shell, that is n equal to 3. We have 2 3s and 2 3p electrons. So it turns out that the 3s orbital is spherically symmetric with no angular dependence and is positive everywhere. So it can hold 2 electrons with opposite spin according to the Pauli's principle that we have discussed earlier. So there are 3p orbitals which are mutually perpendicular. So these are shaped like dumbbells, as you can see in the figure. So these are shaped like dumbbells with a positive lobe and a negative lobe. So the 3p subshell can hold up to 6 electrons but in case of Si it has only 2. So in a Si crystal, when we bring individual atoms very close together, the S and P orbitals overlap so much that they lose their distinct character and lead to 4 mix-up sp3 orbitals. The negative part of the p orbital cancels the s type wave function, so while the positive part enhances it, thereby leading a directed bond in a space. So all these are shown in this figure. So these linear combination of atomic orbitals, that is LCAO, linear combinations of atomic orbitals, or hybridized sp3 orbital point symmetrically in space along 4 tetragonal directions. So to find the location of electron, so we can approximate and calculate probability of finding an electron. So we can use Schrodinger wave equation. The Schrodinger wave equation, which originates from classical mechanics and is a quantum mechanical law describing the energy of an electron. The Schrodinger wave equation, which originates from the classical mechanics. So remember here, it is an electron that is described a three-dimensional wave in the electric field of a positively charged nucleus. The probability of finding an electron at any point around the nucleus can be determined by the help of this Schrodinger wave equation. So we know the basic equation. The total energy is equal to kinetic energy plus potential energy, that is energy of an electron. This is classical mechanics. So E is equal to P square by 2m plus V. So we apply a quantum form. So that is h cross square by 2m del square psi plus V psi is equal to minus h cross by j d psi by dt, where del square psi is equal to d square psi by dx square plus d square psi by dy square plus d square psi by dz square, where h cross is h by 2 pi. So here h is a Planck's constant, E is total energy, V is potential energy, psi is the amplitude of a wave, or it is a wave function. Del is a Laplacian operator and m is a mass of electron. The wave function psi in this equation includes both space and time dependencies separately and combine them later. So given some potential field, the solution of the Schrodinger equation is a wave function psi which describes the location of an electron. So we can take a boundary condition V of xyz. So V is the electrostatic potential field, that is the atomic structure of the material determines the potential field. If we apply a boundary condition to the Schrodinger equation, the wave function psi of xyz, so different coordinates, this describes the location of an electron. So the electron configuration determines the electronic properties of a material. So it is the only particle that is modeled as a wave. Their charge is particle, meaning is that the position of the electron is represented as a wave, but once the electron is found, all of its charge will be in that location. So what does it mean if electrons are represented as a wave? So the atomic orbital is a wave function, describes how electron is distributed around the molecules. So molecular orbital wave function is the distribution of electron over all the nuclei of a molecule. If a molecular orbital is large near an atom, this is high probability finding electron near it. If it is 0, there is no chance of finding electron there. So whatever earlier I have given the example of the mother and the son, so this is that one. If a molecular orbital is large near an atom, there is a high probability of finding electron near it. If it is 0, there is no chance of finding electron over there. So in linear combination of atomic orbitals, that is LCAO approximation, each molecular orbital is constructed from a superposition of atomic orbitals belonging to the atoms in the molecule. So the size of the contribution of an orbital from a particular atom indicates the probability that the electron will be found in that atom. So the actual shape of the molecular orbital is a reflection of the extent to which the individual atomic orbitals interface with one another, eitherly constructively or destructively. So this is the fundamental of the electrons. So to study the further things, you need to know all these things. Thank you for watching the video. If you have any doubts, you can post your comments.